Hi, this is Jason Molesky. In this example, we'll take a look at power models and logarithm transformations. On July 31st, 2005, a team of astronomers announced that they had discovered what appeared to be a new planet in our solar system. They had first observed this object almost 2 years earlier using a telescope at Caltech's Palomar Observatory in California. Originally named UB313, the potential planet is bigger than Pluto and has an average distance of about 9.5 billion miles from the Sun. Now, for reference, the Earth is about 93 million miles from the Sun. Could this new astronomical body, now called Eris, be a new planet? Note at the time of discovery there were 9 known planets in our solar system. So here are the data on the distance from the Sun and the period of revolution of those 9 planets. Note that the distance is measured in astronomical units, or AUs. These are the number of Earth distances the object is from the Sun. Now also note there appears to be a strong curved relationship between distance from the Sun and period of revolution. So as distance increases, the period of the revolution increases as well. The graphs below show the results of 2 different transformations of the data. We want to use these to explain why a power model would provide a more appropriate description of the relationship between period of revolution and distance from the Sun than an exponential model. Well, first, we note that in this first scatter plot, distance versus the natural log of the period, we see there's a clear curved pattern. So an exponential model certainly would not be appropriate. Now, looking at the natural log of the distance versus the natural log of the period, we see that we have a strong linear pattern, which indicates that a power model would be more appropriate. So, Minitab output from a linear regression analysis on the transformed data natural log of distance versus natural log of period is given below. Let's use that to give the equation of the least squares regression line, again defining any variables that we use. Now keep in mind, when looking at Minitab output, we generate the equation of the least squares regression line in the coefficient column. And we'll have to make sure we do that using the variables that we had used to generate this particular output. So our x variable is natural log of distance. The coefficient is 1.499, so that would be the slope of our least squares regression line. The constant value, 0.002544, is the intercept. And we're predicting the natural log of the period. Now, using that model, let's predict the period of revolution for Eris, which is 9.5 billion divided by 93 million, or 102.15 astronomical units from the Sun. Well, we'll plug that distance in. Natural log of 102.15 times 1.49986 plus our constant 0.002544 gives us a natural log of period of 6.939. To figure out the actual period, we use the fact that the natural log has a base of e, so e to the 6.99 or 6.939 is approximately 1,032 years. Now, a residual plot for the linear regression from part B is shown below. Do we expect our prediction in part C to be too high, too low, or just right? Well, note we've got a pretty strong curved pattern here to our residual plot. Eris's value for the natural log of the distance was 6.939, which would fall way to the right of the residual plot, and we note that the residuals there would most likely be positive. So because the residual is positive, and it's the actual minus predicted value, we would expect our prediction to be too low. Now for some additional practice with power models and logarithm transformations, try exercise 43.